So I wanted to work through an example using the conservation of momentum formula that we see in the box right here, which tells us that the initial momentum of the system has to be equal to the initial momentum of the system after the collision. So that's the formula that we're going to be looking at. Now, if you tend to get some of these values mixed up or in the wrong spots, I would recommend that you start off by making a list of your values and you separate them into two columns for initial and final, and then you put the mass 1, velocity 1, so that would be the mass of object 1 and the velocity of object 1, and then the mass of object 2 and the velocity of object 2. So put those down the center, and then we're going to record the values associated with each of these items. So it starts off with a ball of unknown mass has a velocity of 2.3 meters per second. So that would be our unknown mass, means we're going to have x for our initial mass 1, and then the velocity of mass 1 is going to be 2.3. Okay, it tells us that it strikes a 4.2 kilogram ball that was moving at negative 1.4 meters per second. So that's going to be our object number 2. So the mass of object number 2 is 4.2 kilograms, and its speed was negative 1.4 meters per second. Okay, after the collision, the 4.2 kilogram ball has a velocity of 1.6. So that was object number 2. Its mass is still 4.2, but now its final velocity after the collision is 1.6. Okay, and then the ball of unknown mass has a final velocity of negative 2.1, and our mass is still unknown. Now, once you get your information set up like this, what you need to recognize is that all of the values in the left-hand column here, the initial column, those will go into the variables on the left-hand side of your equation, and on the all the values in the right-hand column will go in for the values on the right side of your equation. So that's one way you can try to keep them organized. So it says we need to take mass 1 times the velocity 1 for the initial. So x times 2.3 plus mass 2 times velocity 2 for the initial. That's going to be those two. So 4.2 times negative 1.4. And that is going to be equal to mass 1 times velocity 1 of the final. So that's going to be those two values. Plus mass 2 times the velocity 2 final. And now we have all of our values in their appropriate spots in this equation. At this point, what I'm going to do is I'm just going to start simplifying some of my terms. So I can't do anything with the x times 2.3. I am going to write it in a more standard type of format where we put the x at the back of our coefficient. I'm going to multiply out 4.2 times negative 1.4, and that gives me a negative 5.88. Okay, similar to the right side, I'm just going to rewrite that as negative 2.1x, and then I'm going to take 4.2 times 1.6, and gives me a 6.72. Now I need to move all of my x's to one side of the equation, and then all my constants to the other side. Well, since the 2.3 that is attached to my x on the right-hand side here is a positive value, and this side is a negative value, I'm going to move the negative 1 over to the positive side. So I do that by using inverse operations. So I'm going to add 2.1x to both sides, and that's going to give me 4.4x. Let me change that color. Okay, so 4.4x plus a negative 5.88 equals 6.72. So I've moved my x's over. Now I'm going to move my constant that is on the side here with the x. I'm going to move that to the other side, and I'm again going to use inverse operation, so I'm going to add 5.88 to both sides. And then that is going to give me 4.4x, because those cancel out. And let's see, 6.72 plus 5.88 is a 12.6. And now the last thing I need to do to get x by myself is to divide both sides by 4.4. So 12.6 divided by 4.4. That's going to leave me with x is equal to 2.8636, etc. And again, we were finding the missing mass. Let's check our significant figures. It looks like we have 2 all the way around. So I would record this mass to 2 significant figures as 2.9 kilograms was the mass of the unknown ball.